See that lecture, solved examples they posted after the lecture. That's the one I'm talking about. The second example of the torque. That's the second example. And which part is supposed to care about part B and C? One. You a minute? That's when you how you calculate the efficiency by dividing the output power by input power. That's the relationship between efficiency and output. And there's something called the developed power. The developed power is equal to the out power plus the copper loss. There are many ways to calculate the output power and the input power. When you go to the flow, the power flow diagram here, that's how the power is going. Start here with the prime mover, and then some losses here. All these losses, constant losses, we can add them together and call them rotational loss. All these three little things here, that's the total rotational loss, that's constant. And then you go there, that's to call it the developed power. That's where the mechanical power will be converted into electrical power. That's important part. That's what the generator is going to use. Then what happened? You have copper loss, and then you get the output power. So it's important to know that the output power is equal to the copper loss plus I'm sorry, the developed power. You subtract the copper loss, you get the output power. So this is the developed power. What is the developed power? It's the mechanical power converted to electrical power inside the generator, but just minus the losses, the rotational losses, of course. That's the important fact. So that's how you can get it. Okay?
So the mechanical power.
The shaft, the prime mover coupled with the generator, that's the input power. That's the torque time the speed.
So
give you the input power, mechanical power. Yes.
Mechanical is not the output, different.
No, it's generator. You get electricity.
Oh,
Yeah.
so it's the input.
It's the input, yeah. Right. The lecture. So, and I will post the about answer for you today. Last time we started something very important that when a generator connected to a power system. So you will hear a lot this terminology. You hear a lot this terminology, infinite pass. Infinite pass. Usually the generator is connected to infinite pass. What does it mean, infinite pass? Infinite pass, it means it's a power system so large that its voltage and frequency remain constant, whatever happens. Change in the load, change in the generation, just they keep the voltage and the frequency constant at this bus. And it's called infinite bus. And that's the way to represent it, infinite bus like that. It's very important in power system. So I will just go ahead and review quickly what we did last lecture and the end of last lecture about how to calculate the power using something called power angle or torque angle. Very important. That the armature resistance is equal 0. And only they consider the synchronous reactance, XS. They ignore RA in most calculation. When you go in the power system, find you write XS everything. Even transmission line, they're represented by reactance because it's bigger than the resistance. So if we assume in armature resistance is equal 0, it means we are ignoring the stator loss, a couple loss in the stator. In this case, we can say that the power is equal to the mechanical power, right? Because if you ignore that, how you calculate the power output here? You will say that the power coming here that's converted from mechanical to electrical, and then minus the couple loss. If you don't have resistance, so you don't have couple loss, so this power coming here from the rotor or the developed power, it's equal to the output power equal to this mechanical power. All right. In the end of the lecture, that in the end you can find that the power using this formula, which is really important. What it is? The power is equal to, forget now about three means three phase. The voltage, the terminal voltage VT, and the internal voltage EF magnitude, multiply the magnitude, divided by XS without J. That will be the maximum power, sine delta. What is delta? That's very important, delta. Delta is the angle between EF and VT, the terminal voltage. And usually, we assume that the voltage at the infinite pass or the terminal of the stator are on angle 0. So actually, delta is the angle of EF, the internal voltage. So if you make a phasor diagram, you say if this is VT, that will be EF, and that's delta. Or in the top, it depends. It could be delta. You ask me, is it positive or negative? It could be positive, but negative depends if it's motor or generator. I'm going to talk about that. So the power is equal to 3 VT EF over XS sine delta. So when you sketch this curve like that, that will be like that. Here you go. That's also power. It can be representing power or torque. I will explain that now. So when it's generator, delta is positive. When it's motor, delta is negative. So in this half, right half, that will be the terminal voltage, and delta is positive. It means EF is leading the terminal voltage. That's generator. If it's motor, you got VT, and then you got EF behind by delta. What is delta is called? Delta is called power angle, and also they call it torque angle. Why? Why they call power angle first? Well, look at that curve, the power here. We proved just P is equal P max sine delta. P max, we just said, is equal to 3 V terminal magnitude times EF magnitude divided by XS. That's the max power, if you want to get it. When it happened, max power at delta equal 90 degree. At 90 degree, that's the max. How you find the torque? Very simple. Find the torque, because we ignored the losses, said the power divided by this. Oh, that you got it. That's the power. VTEF over XS sine delta, and that's the max power. If you divide that by omega, then you get the torque. And that will be, so the torque equation will be the same thing, just divided by omega s. That's all. So that will be the T max. That's why they call also delta torque angle, because it's in both equations, in the power equation and the torque equation. So that's the equation of the power, and that's the equation of the torque, the same thing. So the power is equal P max sine delta, and torque is equal T max sine delta. What is divided by omega s? So that's how we calculate the power. And they call 90-degree the static stability limit. What does it mean? As I explained last lecture, that you cannot go beyond 90-degree or the system will lose its stability. Right? The same thing for the torque. That's why the max torque, they call it sometimes pull-out torque. Okay. To find Q, we did Q last time by the same, and you'll be able to derive the equation. That's the expression for the reactive power. Let's look at it. It's equal to 3 VT EF over XS, exactly like we did in the power, but this is not sine delta. Cosine delta minus constant term 3 VT squared over XS. These both formula will prove it last lecture. Should be able to do it. Well, what's B? What's Q? P are the power, the active power and reactive power at the terminal at VT. So you can look at it, the generator, sending power and reactive power to the infinite paths where the load is connected. So the power is received. So the power sent, the power received, you're equal. Why they are equal? Because simply you don't have resistance in the middle. We ignore RA. And if there was RA, there will be losses, couple losses. So the output power going to the infinite paths will be equal to the input power coming from the generator minus the couple loss. But in this case, very simple. The input and the output are equal as a power. Q, different story, right? Because there is X here, the XS. So some XS, because X related to the active power. So there will be difference. The difference between the reactive power at the receiving end and the sending end, the reactive power taken by synchronous reactance or reactance connected between both. So you got two formula to find power, active power, reactive power. You got two formula. The first formula, the simple one that you know, let me get it here for you. Yes, that's the power. You multiply the voltage by the current by cosine the angle between them, the power factor. That's what you know. And if you want to find the reactive power, it will be equal 3 times VT IA instead of cosine phi sine phi. That's what you know, how you find the active power and reactive power. That's one way. Another way, using EF, using we call it the two voltages, not voltage and current. Here you are using voltage terminal and the armature current. Here you are using one voltage here and one voltage on the other side. And this one for synchronous generator connected to infinite bus, but actually they use it in any source connected to another bus. It doesn't have even two generators. Just if you have any system like that, can represent as a voltage source, and you have bus bar or infinite bus and transmission line, always represented by X, as I said, JX. If you want to include also the synchronous reactance of the generator, and then you have the reactance of the transmission line, call it T, and then you got the terminal voltage. In this case, you make the equivalent circuit. Let me show you how you do it. In this case, you are going to make it like that. You will say that's the generator. That's how you represent the generator. Ignoring the resistor. And that's the terminal voltage. Now, let's say that you are not connect the load directly, which makes sense because we'll have transmission line. And then that's the transmission line. And then you have load. You connect the load at the distribution. So this one transmission line, you can represent by many things. If you have power cores, you can represent by resistance and reactance and capacitors. It's complicated, but always when they do the analysis on power load flow, they just represent by X, by reactance, and it gives good result. Let's call this transmission line reactance. So you are going to add another thing here, J, XT. And then the employment bus, where is the load, then you can put the load. So what we'll do now, see, that's now not the terminal voltage of the generator, that's the terminal voltage of the generator, but now we deal with it like generator and terminal voltage. So call this one VT. So now you have source and you have the terminal voltage, you can make it like that, and you have X and X between them, the sum of both reactants, you can call it JX, where X is equal XS plus XT. And then you can calculate the power delivered to the load, not using current. You can use, of course, current, but using what that I'm doing right now. The power delivered to the load is equal to 3, the EF for another voltage, and the other voltage VT for X only, sine delta. What is delta? Delta is the angle between this voltage and this voltage. And sometimes you will see that a lot. Okay, you don't have generator, you have two bus bar, and both bus bar you have two different voltage. For example, that's bus bar 1, bus bar 2. The voltage here is V1, the voltage here is V2. What is the power delivered to 2? From 1 to 2, 3. Now I modify just the same way. The voltage V1 times V2 over X sine delta. What's delta? Delta is the angle between V2 and V1. So that's V2 and that's V1. So we deal with it like exactly like generator. You deal with any voltage source now, just in the power system. You want to find the power in any side, you use this one all the time. Okay, so that's two formula for power and reactive power, very important between the two voltage, used in power a lot. And this is the normal way at the load when you want to calculate using the voltage and the current and the power factor, the angle between the voltage and the current. Okay. And we said that this 90 degree, it's the static stability limit that we should not exceed it. That positive angle when it's generator, positive angle, what angle I'm talking about? I'm talking about delta, the torque angle or power angle, all right? And that's what you said, if delta exceed 90 degrees, the synchronous generator lose synchronous or be out. Let's assume we have a network and then there is one generator that the delta exceed 90 will be out of the system, like it doesn't exist. And this was the only generator, the city will be off, will be dark. So that's important to keep it at the limit 90 degrees. Okay, let's take here one example and solve. Let's just read it first and then see how we're going to do it. We have a three-phase generator and a apparent power is given, the line-to-line voltage, 4 poles, 60 hertz, the all information given. And the synchronous reactance is equal 8 ohm, all right? The machine is first operated as a generator in parallel with three-phase bar supply, all right? Determine the excitation voltage. So everything is given, and you want to find EF. When they say excitation voltage, mean EF, not angle and magnitude. No, means magnitude when they ask about the excitation voltage. And the power angle, what does it mean? You want a delta. So when the machine is delivering rated kVA, 0.8 voltage, so the power is given, all right? And you want to draw the phasor diagram at the same time. So let's do the first part, how to find the EF. How to find the EF? Let me first sketch the equivalent circuit here. That's how you can find the voltage. You got synchronous reactance was given is equal to J8. So it's J8. And you want to find EF. That's EF. And it's given everything for the load here across the stator terminal. They said that delivering rated kVA. All right. The rate kVA S rated was given equal to 5 kVA. So it's like 5,000 volt amp. And the terminal voltage line to line it was 208 voltage. So when you talk about VT here, it got to be phase voltage, right? So VT phase will be equal to 8 divided by square root 3, which is equal to 120 voltage. And usually we take it to an angle 0 as reference. Well, we need now to find the current IA. How to find the current IA? He said rated voltage, and the power factor, I'm going to show you here. That's the rated kVA and 0.8 power factor. So I can find the current. How you find the current? First, I find the magnitude of the current. The magnitude of the current will be equal IA. Magnitude is equal S, which is equal to 5,000 volts amp divided by square root 3 volt line, which is 208. I have it here, times 208 voltage. So you get the amp. It will be equal 13.9 amp. That's the magnitude of the current. I want to find the angle. How I find the angle? Using the power factor. We did that like 100 times, right? So the angle phi is equal cosine minus 1. The power factor, which is equal 0.8, is given. And if it's lagging, so you put just negative sign. Yes. Because, okay, that's a good question. Because you know that S for a three-phase, you got two options. Square root of 3 VL IL, or 3 times voltage phase times I phase. So which one you're going to use? Whatever, both are right. I have the rated bar S. I have the line to line voltage was given 208 in the problem. Said yes, but you got it here in phase 120. If you want to use 120, so you don't say divided by root 3, divided by 3, because I'm using this or that. Okay. All right. So that's why we got the current magnitude. We got the current now angle using the power factor will be minus 36.9 degree. So that's the angle. So now we can represent the current as a phasor. IA is equal IA magnitude 13.9 and the angle negative 36.9 degree. And that's the current. Yes.
This is the equal.
They are equal because always, if it, that's a good question. If it's not mentioned, the time connection, it always assumes Y connection. Yeah, Y connection, star connection, line current equal phase current. The problem only with the voltage, because most generators are like that. But yes, if it's delta, then you got to take care of it. Yeah. So I got the current. Why I got the current? Because in the equivalent circuit to find EF, he said the terminal voltage VT plus the drop across XS, right? So I will say now, solving it algebraically, I would say EF plus JXS times IA. And by the way, just let me mention now, this equation is valid for generator. If you have a motor, you have the same equivalent circuit. If you have synchronous motor, you will have the same equivalent circuit, but will be different. The current will be reversed, and the machine will be supplied by electrical energy and going another way. So this equation will be like EF equal VT minus. That's right. Okay. Anyway, we are now in the generator mood here. So we'll say that EF as a phasor is equal VT, which is equal 120, we already got it, in angle 0, plus J8, which is the reactance, times the current. We got the current is equal 13.9 angle negative 36.9. Doing that and then make the calculation, I got EF is equal 206.9 an angle 25.5 degree. So that's EF. The question is find the excitation voltage. So let's say excitation voltage, that's excitation voltage. 206.9 volts. That's the answer. Find the torque angle or power angle. So power angle, it's delta. It's 25.5. So just it's important also to how to extract the information here. How you do the phasor diagram? We did that last lecture, but let me do it again. Well, that's the terminal voltage. Always will assume it's the reference. So that's VT, which is equal to 120 volts on angle 0. And the current, it's given an angle negative 36.9. So just let's say that this is the current. And the current is equal to 13.9 amp, and the angle is equal to 36.9, and it's negative. Now you want to find the drop. Look at the equation here. I want to understand VT plus JXIA. So you need to find JIA. JIA, and then multiplied by X. So what is JIA? J, it means angle 90, plus J plus 90, minus J minus 90. So let me do it on the side here. So when you have, if you have J like, if you have current I like that, so what is JI? 90 degrees, that's JI. What is minus JI in the other direction? All right. You have here JXIA. So that's I. If you make that, if you extend this, the line of the current, that's I. So what is JI? Will be in this direction, right? So if you make a perpendicular line to this one, so and you continue here. So this red line, the solid red line, you can measure your XSIA. What's XIA? The drop here. XSIA. And tell me what is J? I already make it perpendicular to the line of IA. So that's the same direction. So let's just to say, okay, that's for example, that's the length up to here only. Let me choose another color, right? So I know what is the direction. So I said that when I measure that's enough. Multiplied XS by IA. So that's XS, which is 8 times IA, the value only, not the angle. The angle taken care of, times 13.9, and I get the value. Then what happened here? That's the result. I connect from here to the tip. So now it's vectorially like VT, when you look at it, that's the terminal voltage, and then I added JXS. So what you got here? EF. So that's your EF. So that would be your EF, magnitude angle. You measure it and you see the angle, then this is your delta. So that's how you do the phasor diagram. All right. So we did calculate the excitation voltage and the power angle. And now let's go for the second one. If the field excitation current is now increased by 20%, excitation current, we didn't talk about any field current here, right? Now it just increased by 20% without changing the prime mover power. What does it mean? I want to understand every single word in this problem. What does it mean that you don't change the power of the prime mover? The prime mover that's rotating, giving the energy to the machine, to the generator. So if you don't change the power of that turbine or the prime mover, it means you still taking the same power. Why? Because the output power is equal the input power minus the losses, rotational losses. There is no copper loss. We agree about that. So and rotational losses always will assume it's constant. So if you keep the prime mover doing the same power, so you're still taking the same power. So what does it mean? Power is constant in this case. So all right. So power is constant. Field current increased by 20%. Find the stator current, the power factor, and the reactive power supplied by the machine. Step by step. You want to find the stator current first. All right. How you find the stator current? Think about how you find the stator current in this situation. Let me go. That's the circuit. Now the current is not given, is unknown. Yes, you get the same power. Like whatever power that you got here, let's say they got 300 watt, you will still take in 300 watt, but change. Let's go remind you by the equation I told you about the power. Power is XS sine delta. You're still taking the same power. You'll take the same power. If you take the same power, can you tell me, did you terminal voltage It's changed? No, we just said in the beginning of the lecture, when you have infinite paths, you always keep the voltage constant. You want to keep this voltage 110 volt, right? So that's constant. What about the reactance? Does it change? No, constant. And the power, constant, because you said that you keep the prime mover moving. You know? So what is it changing here? Two things, EF and delta. Well, they said that the current, the field current, what is the effect of field current? Curve, it's the relationship between IF, the field current, and the voltage, the induced voltage. So if you increase IF, you will increase EF. So this going to change because EF is proportional to IF. And we did that many times about the magnetization curve. Let me just refresh your memory. And you're going to do one this week. The synchronous generator, we are going to do the magnetization curve too. So that's the magnetization curve. What is this axis? That's EF. So if you are working at this current, IF1, what you'll get here, you get EF1. If you are working on another current, you increase the current to IF2. So what you'll get, EF2. So proportion. So you can say that EF1 or EF2 divided by EF1 is equal to IF2 divided by IF1. They said increase it by 20%. So what does it mean? It means IF2 over IF1 is equal what? Increase it by 20. If IF1 100, just to always think about that. So what's going to be IF2? 120, right? So IF2 over IF1 equal to 1.2. True? All right. So now we'll say that is equal to 1.2. So what is EF2? The new EMF is equal 1.2 times EF1. The value of EF1 before? Yes, we do. We did the excitation voltage. We found that the value that we got last time, 206.9 and the angle 25.5. Then you tell me, when I do this ratio, should I use also the angle? No. If you look at the curve, you don't use any angle, only magnitude. So actually, this is the magnitude. So D1.2 times, it was, I think, 206.9. Let me check. Yes, 206.9. And then we calculate the new value of the excitation voltage. Okay, so somebody can calculate X2. With this element, nothing? So, okay. So that's EF2, I got it. So what next? Remember that they said the power is constant here. I want to tell you some information from, if you have constant power, and this is happening a lot, is equal EF XS sine delta. If it's constant, K. So, and we said this is constant, and this constant, what's left? It means EF sine delta is equal K time what? Time KS. I'm just using this equation to find EF sine delta. KS over 3 VT. Constant, all that constant. So what I'm trying to say now, I'm trying to say that EF sine delta should be constant if the power is constant, and you're only changing the field current so that you will have it. You always keep EF sine delta constant. All right. Well, in this case, you can find the new delta. If you have the old information, you can find the new delta. Why? Because EF sine delta equal constant. So what does it mean? Yes. A times XS divided by 3. Just I'm solving this equation.
Is that VT in the denominator?
F VT sine delta, that's in the top, that's VT. Yeah, terminal voltage. Yeah. So if EF sine delta is equal constant, so what does it mean? It means that you can say that EF2 sine delta 2 F1 sine delta 1 equal EF3 sine delta t, and so on. All right? It's constant. We just prove it's constant. From this equation, I can get the value for delta 2. So you can say sine delta 2 is equal to what? Equal EF1 sine delta 1 divided by EF2. EF1, we already got it. We know it from the first time, it was 206.9, and delta was 25.5, so the sine 25.5 divided by EF2, we just got it, 248. From that, we get the value for sine delta 2, and so we can get delta 2. So delta 2, we got it is equal to 21 degree. So we got the new voltage, EF, 248, and we got its angle 21 degree. So if you keep the power constant, the only thing that you are changing the magnitude EF sine delta. Sine delta always will be constant. But the question is, find the current. So why you did all that? Simply because when you have the equivalent circuit, how you find the current? You know the equation here, EF equal to V terminal plus J XS IA, right? So if you want to find the current, you will say IA is equal to what? EF minus VT divided by JXS. So to find the stator current, you got to have EF, VT, XS. You have VT didn't change. XS didn't change. EF changed. That's why I was working on finding EF, the new EF. That's why. And I found its magnitude and its angle. So now I can find IA. IA would to EF minus VT divided by JXS. EF, new one. Now, I'm talking about the second. EF2, the magnitude is equal to 248 with angle 21 minus the terminal voltage is constant, it's 120 on angle 0 divided by J8, and you get the stator current. We read that's equal to 17.86 on angle negative 51.5 M. So that's the new stator current. So that's how you got it. So stator current, to get stator current, you got to have two voltage, VT and EF. I have everything except on EF. That's why I was working on EF. Then the second question is to find the reactive power Q. How you find Q? One, as I said before, that Q, you have always two formulas. The first one is 3 V terminal magnitude IA magnitude sine phi is the power factor. Well, and the other one that we got it using both voltage, you can say 3 VT XS, not sine for the power, right? And cosine for the Q, and we said minus constant term, it's VT square over XS, and you have 3 here. So you got this formula or this formula to find Q. This is the first one because you have everything there. Then, but you got to remember, power factor is not fixed in this case. When the magnitude of the current changed, phi changed. So you got to get, that's your new phi. 51.5. That's your new file. So I will just use the top one. It's easy. I have the terminal voltage is equal to 120. I have the current already. I have the magnitude 17.86 and sine, and the angle is 51.5 degree, and they get the reactive power. It's there. So to F 03 kVA. But the idea is not just solve get number. We want to know the effect of the field current when it increase. So let's make the phasor diagram. First, I mean, you understand the phasor diagram, the first case, right? That was the current was lagging the voltage terminal, and you got the EF and this delta boss and everything. Now let's do this new thing, the new voltage. I'm done, right? Just 1 minute. That's the voltage. That's the last thing, and we're done. That's the voltage. And observe here the current, what happened. It's negative 21, all right? Will be 17.86. Continue here, and you get the new value for the power when you get. Well, we'll continue next time. We're done with the time.